Welcome to part 2 of the lecture on pain. In this bit, we're going to talk about the factors that physiologically change the experience of pain. So first off, we're going to look at the general mechanism of referred pain, and then we're going to look at two mechanisms that can modulate or inhibit pain. So they're anti-nociceptive, anti-pain if you like. Finally, we'll look at sensitization, and sensitization can happen peripherally at those free nerve endings or centrally at the synapses. And it's that sort of central sensitization that we talk about when we talk about long-term potentiation of pain, LTP, or also can be referred to as neuroplasticity. These are long-term structural changes. Remember that many neurons make a nerve, and that ultimately the nerves combine to form the spinal nerves. Therefore, within each spinal nerve, there'll be sensory afferent neurons from different areas. In referred pain, a primary sensory neuron from a specific organ and a primary sensory neuron from an area of the skin share a second-order afferent neuron. Both primaries synapse in the dorsal horn with the same second-order afferent, and that then ascends via the usual pathway to the cortex. Consequently, the sensory cortex can't identify the origin of the pain. It can't tell if it was the organ or the area of skin that stimulated the pain or transduced the pain. Possibly because the skin is more likely to be damaged, the sensory cortex will sometimes perceive the pain as coming from the skin instead of the organ. Here you can see two primary afferent neurons. These are the ones in yellow, one from the kidney and one from the skin. Look at the dorsal horn. You can see that both synapse with the soma of the second order afferent, the one in red. There is only one ascending neuron. Therefore, how could the cortex know where the pain came from? Because the neurons sharing this way have been identified and are often talked about as dermatomes, we can map the likely sites of pain related to specific organs. Of course, one of the most well known is the heart and the skin of the left arm and shoulder, or of course the gallbladder and the right shoulder. There are two mechanisms of modulation, gate control and descending modulation. We can describe both of their actions as anti-nociceptive. In other words, they are mechanisms that reduce pain by inhibiting the pain pathway, ultimately where the second order afferent receives the EPSPs from the primary that transmits the action potential. First, we'll look at gate control. Gate control occurs at the spinal cord level. It inhibits the creation of an action potential in the second order afferent. It involves a beta, not a delta, a beta fibers. A beta fibers are not nociceptive. They detect non-noxious mechanical stimulation, such as the skin being rubbed. This modulatory pathway, gate control, is all at the level, at the dorsal horn level, at which the afferent comes in, the primary afferent comes in. So we have our primary afferent coming in. So here's, for the sake of I suppose, example, we'll make it a C fibre. could be an A delta, we're going to make it a C fibre. So that's coming in, and as we know what it does, it then synapses with the second order afferent that goes on up the pain pathway, thalamus, sensory cortex, etc. So that's our normal pain pathway. Now, A beta fibres, not delta, A beta fibres are slightly different. These actually detect touch. They're not nociceptive. So they detect normal touch that you get, for example, on your skin. Now, the A betas can have an impact on our second order. So to do that, what we actually need, or we'll have it in red, we can have, remember our old friends, the little diddy interneurons. So we can have an interneuron. This interneuron is an inhibitory interneuron. Inhibitory interneuron. Remember, all this is happening within the dorsal horn, at the dorsal horn level. And there we had our, let's label it, our A beta fibre. Just for the sake of argument, let's put a mechanoreceptor on the end of it to show that it responds to touch, not pain. Okay. So let's think about this. We want our A beta inhibits this pain pathway via an inhibitory interneuron. Remember, with inhibitory interneurons, what we need to do, we need to stimulate them. So here, our C fibre, that produces an EPSP in our second order neuron. The A beta fibre creates an EPSP in our inhibitory interneuron because it needs to stimulate it for it to work. If you didn't stimulate it, it would just sit there doing nothing. So we have two EPSPs. The inhibitory interneuron, on the other hand, at the other end, what it does, it creates in our second order afferent an IPSP, inhibitory postsynaptic potential, using the neurotransmitter GABA. Remember GABA? Of course, here we've got glutamate. Here we've got GABA. Creates an IPSP in the second order afferent. And you can see what's going to happen here. What happens, summation, we've got an EPSP, we've got an IPSP. They negate each other, don't they? So when we get to summation, what we're not going to get is an action potential in our second order afferent. So our C fibre sent in an action potential, I've got pain. Second order afferent says, sorry, it's been blocked by this inhibitory interneuron that was stimulated by an A beta that responds to touch. So what's the first thing you do when you get pain? Oh, I've hurt my leg. You rub it. My tummy hurts. You rub it, you hold it. And that's exactly what you're doing. You're stimulating the A betas to stimulate this inhibitory interneuron that blocks the pain by producing IPSPs in the second order afferent. And this is exactly the way TENS works, TENS machines. They stimulate A betas to try and block the pain at the second order afferent. And this is gate control. Because Because the EPSP from the C fibre is inhibited by an IPSP from an inhibitory interneuron, which in turn is stimulated by the A beta fibre, the pain pathway is inhibited. This is why we rub painful areas. What we're doing, we're trying to stimulate those A beta fibres to inhibit the pain pathway. This is also how TENS works. Oh good, a more complex mechanism. I'll try and make it as simple as possible. So descending modulation does as it says on the tin. It descends from the limbic system and or the cortex. It's therefore an efferent pathway. Modulatory action potentials are received in the midbrain, in an area known as the periaqueductal gray, or PAG for short. In the PAG, there is a complex interaction of excitatory, inhibitory, and inactive interneurons. These are sometimes referred to as on or off switches, or as silent switches. The inhibitory interneurons, the off switches, block modulation from progressing down to where it can have an effect on pain. So they need to be turned off. Antinociceptive, in other words modulatory action potentials received in the PAG, stimulate off switches, that is inhibitory interneurons, to exocytose enkephalin. You may know of enkephalin as an endogenous opioid. It acts as an inhibitory neurotransmitter in the PAG. Enkephalin from the inhibitory interneurons actually inhibits other inhibitory interneurons that act as off switches or blockers in the modulatory pathway. Basically, the whole process turns off the off switches. Therefore, modulatory action potentials can be chemically transmitted in the PAG and sent down via efferent neurons to the medulla. The efferent modulatory neurons synapse again in the rostral ventromedial medulla, or RVM. That's just a section of the medulla in a position near the front. The next efferent progresses down to the dorsal horn, at the level at which the primary afferent of the pain pathway is entering. The neurotransmitter of choice here is serotonin. Remember we said that neurotransmitters themselves are not necessarily excitatory or inhibitory. It all depends on a specific receptor. Well, in descending modulation at the dorsal horn level, this is exactly the case for serotonin. Serotonin has many receptors, often with completely opposite effects. So when exocytosed by the final modulatory neuron, serotonin can directly inhibit the ascending second-order afferent by creating IPSPs in that second-order afferent. Or it can create an EPSP in an inhibitory interneuron, which then creates an IPSP in the second-order afferent, a bit like the inhibitory interneuron of gate control. Let's look at all of that on the whiteboard. Okay, so we're going to talk now about descending modulation. We've talked about gate control. This one is all about modulation that is coming down an efferent pathway from the cortex and the limbic center. So, okay, if we look at, first of all, our incoming, if you like, our afferent pathway. I need to leave a bit of room for me modulatory. Oh, look at that. That's a terrible dorsal horn, but you get the general idea. Okay, so our afferent pathway coming in. Here's our little nociceptors. Here they come, in they come, and here I'm going to need to leave a wee bit of space for this. Off we go, up. That's our normal pain pathway going up to the thalamus and cortex. Yeah. Okay, descending modulation, as we said, it originates, we think, within the cortex and the limbic system. So up here, we'll have cortex and limbic system. Yeah? So this is where we think all this modulation will originate from based on previous experience and what we think the pain, whether we think it's dangerous, that sort of thing. Very close to that, of course, we have the midbrain, almost embedded within it. So here's our midbrain. Tiny, tiny area, but within that, the bit that we're interested in is that periaqueductal grey, or the PAG. Involved in this pathway, we also pass through, or just pass through, the medulla. Because he doesn't like to be left out, the medulla. And if you remember, that's the rostral ventromedial medulla, RVM. So if you see RVM in text, you know that we're talking about the medulla. And you generally will if in terms of pain. So, okay, our cortex and limbic system, as we said, generates these modulatory action potentials that go down to the midbrain. In the midbrain, we have this in the PAG, we have this sort of complex situation where we've got lots of interneurons, and basically that modulatory pathway will sort of turn on modulation by turning off inhibitory interneurons. So the pathway is normally blocked by inhibitory interneurons or off switches. And what we're going to do is turn the off switches off, which turns the pathway on. So we do that, and we do that, if you remember, through the secretion of enkephalin, the endogenous opioid, and that's why it's an endogenous opioid. So that all happens in the PAG up here. That then travels down, so we'll have a couple of pathways to synapse in the medulla. So the medulla here is really just acting like a bit like our thalamus. It's a sort of relay point. So we have another synapse here. Now we get to some more funky bit. So our last neuron in the line comes down here, and of course it's going to secrete the neurotransmitter serotonin. Serotonin can be excitatory or inhibitory depending on the receptors that it binds to. So in terms of direct inhibition here of our pain pathway, and again, the target is that second order neuron at the level of its soma. Here's its soma. So here we can secrete serotonin and it becomes inhibitory. So what we get is an IPSP. That's not very clear, is it? I said I should leave more space for this. IPSP. Yes? Of course, that's going to counteract any incoming EPSPs from our pain pathway. So here we've got EPSPs coming in. In addition, in its sort of excitatory role, if you like, serotonin can, let's have a little branch off, synapse with an inhibitory interneuron. So here's our little interneuron, that's going to synapse there. There's our little interneuron synapsing with our second order afferent soma. Of course, serotonin here is behaving in an excitatory capacity because it's got to turn on The interneuron, when it turns on the interneuron, however, the interneuron produces an IPSP in the second order afferent. So serotonin can work in an excitatory or an inhibitory capacity. If it's being excitatory, it needs an inhibitory interneuron to convert that. But what it does, it creates IPSPs in our second order afferent. And because it does that, of course, via summation, it's going to block any incoming EPSPs, and we're not going to get an action potential generated to go up to the thalamus and cortex. And that's descending modulation.
Various inflammatory mediators can stimulate pain by binding to chemosensitive TRP channels on the free nerve endings. This is basically transduction by inflammatory mediators. This list is of the more common mediators, but it's not exhaustive, as you can see from the list on the diagram. As in all transduction, EPSPs are created that are then summated by the trigger zone, which may then generate an action potential to the dorsal horn. Inflammation may also result in mechanical changes. That can also stimulate mechanosensitive TRP channels. Via G protein coupled receptors, the inflammatory mediators that cause pain can also increase the likelihood or strength of pain. They do this through the phosphorylation of existing channels or by stimulating the expression of more channels, i.e. upregulating their number. This is a pro-nociceptive effect, as opposed to anti-nociceptive modulation. Peripheral sensitization is increased by chemicals known as neuropeptides that are secreted by the C fibers. These neuropeptides also upregulate inflammation, so they are pro-inflammatory. Branches that leave the afferent C fiber close to the free nerve endings have specialist axon terminals. These exocytose these chemicals known as neuropeptides, as in proteins made by neurons, but not technically just neurotransmitters. Substance P is significant because it not only causes an upregulation of inflammation by degranulating and activating mast cells, remember mast cells secrete cytokines and prostaglandins as well as histamine, it's also exocytosed at CNS synapses, resulting in pro-nociceptive synaptic upregulation. CGRP is a strong vasodilator, and therefore with substance P, through the release of histamine, adds to hyperemia and edema.
Let's talk about inflammatory pain and also neurogenic sensitization, because they sort of go hand in hand. So again, our free nerve endings are down here. We have our second order afferent going off, our first order afferent going off. But in this case, we're going to add some things in. So we have these specialist branches. This is primarily C fibers. And we have these specialist branches that have things like axon terminals on the end of them. They're like axon terminals in that they exocytose chemicals. So there we go. So we stimulate our nociceptors. Here we go. Have a bit of stimulation. Thank you very much. In we go. Action potential goes on. And yeah, we know it goes on up to the dorsal horn and onto the thalamus and the cortex and all that. But it also shoots off down, following the membrane, because let's face it, you've got voltage-gated channels, it's just going to keep opening those channels and get directed down these here. When it gets there, it acts like any other action potential. It's going to cause exocytosis. It's going to open calcium channels, they're going to interact with the cytoskeleton, exocytosis. In this case, what we're exocytosing, though, is something called substance P, SP, and there are a few others as well, calcitonin gene-related peptide, and there's a few others, neurokinin A, but we're not going to focus on those. Substance B and calcitonin gene-related peptide comes out, it's exocytosed around the site where the pain was stimulated. Now, calcitonin gene-related peptide is a really, really strong vasodilator, and we'll talk about it particularly when we look at neurophysiology in relation to headache. But it's a great vasodilator. So we get vasodilation. Because we get vasodilation, of course, then we tend to get edema. So vasodilation and these vasoactive changes give us edema or swelling. Of course, when we get edema and the swelling, you've got these little nociceptors within the tissues. All this swelling is going to press on them. So we're going to get the stimulation of mechanosensitive TRPs. Yep. So that edema is going to stimulate pain due to vasodilation, due to calcitonin gene-related peptide. If you remember the other thing that we said that substance P does, substance P degranulates mast cells, degranulates and activates. Remember, they don't just degranulate histamine, da-di-da-di-da, but they also start secreting, and they start secreting things like prostaglandins and bradykinins, and when we get lots of chemicals joining the soup there. So we get, of course, histamine. So histamine, and what else comes from mast cells? Serotonin. Let's have some bradykinin. Let's have some prostaglandins, PGs, and some nerve growth factor. Oh, look, guess what they do? They bind to and stimulate our chemosensitive TRPs. Yes. So also our chemosensitive. So what we can see here is, of course, you stimulate the nociceptors on C fibers, and what you get is substance B and calcitonin gene-related peptide, the neurokinins, secreted from these specialist axon terminals. And what they do is, not only do they increase pain, so we have increased pain going up to our thalamus, they also increase inflammation in the area because you degranulate mast cells, you get all these chemicals joining in, and you get a general upregulation of inflammation and of pain. So you get inflammatory pain and you get neurogenic sensitization at the peripheral level. In other words, where our nociceptors are in the peripheral nervous system. Centrally, however, we have an additional problem, because up here at our synapses, let's use the same colour. So here's our central synapses, doesn't matter where it is. Could be the thalamus, could be the dorsal horn. Here's our central synapse. The other problem we have when this happens, not only does substance P come out here, it's also then exocytosed into the synaptic cleft. So we get substance P at the central synapses. And what it does there at the central synapses, it enhances the effect of glutamate. It sensitizes the glutamate receptors so that glutamate has a greater action. So it's enhancing pain centrally at the synapses. So this is central sensitization, and peripherally at the nociceptors, this is peripheral sensitization.
So, in acute pain through G proteins, peripheral nociceptors are upregulated by the phosphorylation of channels and an increase in channels. Also, synapses within the central nervous system are upregulated by the additional exocytosis of both substance P and calcitonin gene-related peptide to enhance the effect of glutamate. In the longer term, there are more persistent changes within the synapses and within the neurons, and this causes chronic pain conditions. This is the same cellular mechanism of creating long-term memory, but it results in persistent pain rather than memories. Let's look at how substance P affects the synapses. C-fibre neurons exocytose substance P as well as glutamate into the synaptic cleft. While glutamate binds postsynaptically to AMPAs and NMDAs, substance P binds to NK1 receptors. Via G protein signaling, this phosphorylates the AMPAs and makes them more likely to open, and for longer. Also, the substance P receptors, NK1, on the postsynaptic membrane can be increased. This enhances the effect of substance P when it's exocytosed into the synaptic cleft.
So we have basically our postsynaptic membrane. I'm going to have to leave a massive synaptic gap here, I'm afraid, because we need to put a lot into it. Okay, so here we have our postsynaptic neuron, and here we have our presynaptic neuron. Okay, so as we said, glutamate is our neurotransmitter. So glutamate, in the usual way, action potential comes along, opens voltage-gated calcium channels, exocytosis, in this case of glutamate. So let's have some vesicles. There's our vesicles, and of course, there's our exocytosis, and we'll have some molecules of glutamate. There we go. Diffusing out into our synaptic cleft. This is our synaptic cleft. Okay, on the postsynaptic membrane, in A delta and C fibers, we have AMPAs. So we have channels with a receptor for glutamate. And this is and AMPA. R is for receptor. As I said before, the AMPA you don't want to know, really. This is quite an acceptable abbreviation. We're going to stick with this one. So this is our AMPA channel. And this is the channel that is mainly responsible for creating EPSPs in our postsynaptic neuron and transmitting that action potential. So, AMPA channels, when glutamate binds, there's glutamate binding diffused across the synaptic cleft, our AMPA channel opens, and we get an influx, as you'd expect, of sodium, which gives us local depolarization, in other words, an EPSP. In C fibers, though, we have another one. The AMPAs, they open very quickly, they don't stay open very long, but they do create EPSPs, and really, they're just like our sodium channels before that we talked about with acetylcholine binding or the rest of it at this point. But on our postsynaptic membrane in C fibers, not in A delta, we also have another ionotropic channel and receptors. I say receptors because we actually need two things to bind. And these are our, I need to put a little space in there. You'll see why in a minute. These are NUMDARs. Again, R for receptor, the rest of it you really don't want to know. NUMDAR is fine. Okay, now these channels, they take a bit more to open. Not only do they have binding sites for two different chemicals, so they're chemically gated, they also have a voltage sensor on the inside. So not only are they chemically gated, they're also voltage gated. Now, what they actually need, so glutamate, we'll start with glutamate. Glutamate comes along, glutamate binds in the same way as it does to the AMPAs. But what it also needs is two other things. It needs that depolarization from the AMPAs to hit the voltage sensor, so the voltage sensor reaches threshold. And it's got quite a high threshold, so it needs strong depolarization from the AMPAs before it will do anything. Yes? So strong depolarization, glutamate binding, and one other thing, it needs something called glycine to bind to. So here's, oops, that's a rubbish pen, isn't it? God, me and my pens, eh? Let's have a different green. Glycine. Glycine is just an amino acid. It's an amino acid. It floats around the synaptic cleft. It's got nothing better to do. So when all of these things happen, it also binds. So we've got glutamate binding, glycine binding, depolarization within the postsynaptic neuron. When that happens, the NUMDARs open, and they're really cool. We've always talked about channels. Yeah, they just change shape and they open. NUMDARs, when they're closed, they're blocked by magnesium. So we have magnesium blocking the channel usually. Oops. Mg++. Magnesium is a double cation, a bit like calcium, or iron for that matter. When we get both glutamate binding, glycine binding, depolarization via the AMPAs, magnesium comes out of the channel and opens the channel. Once it's opened the channel, so let's get rid of magnesium, off it goes into the distance. Once it opens the channel, the NUMDARs, they also influx sodium. So we'll have some sodium going in. But not only sodium, they also allow the influx of, blue pen, it's got to be calcium. Calcium. So you can imagine, of course, we've got sodium going in. This is adding to the strength of transmission across this synapse. But we've also got calcium going in, which is a double cation, so even more positive as well. So in minimal stimulation, an AMPA will open, we'll get an EPSP because we've got an influx of sodium. In stronger depolarization, stronger stimulation, we'll get these NUMDARs opening in C fibers that allows an influx of sodium and calcium. And it strengthens that EPSP. So there is more likely to be an action potential in that postsynaptic neuron. And later we'll also talk about the other effects of calcium in terms of signaling and synaptic plasticity.
The calcium influx via NUMDAR channels adds to the depolarization, but it also acts as a signaling molecule when bound to calmodulin. Calcium is also released from stores such as the endoplasmic reticulum via glutamate binding to G protein-coupled receptors on the postsynaptic membrane. Remember IP3? If you also remember, these G protein-coupled receptors on synapses are known as metabotropic. Calcium signaling within the postsynaptic neuron results in changes to the AMPAs, phosphorylation, increased numbers, and AMPA channels that allow both sodium and calcium through. All three potentiate the action of the AMPAs and their response to glutamate, creating more and stronger EPSPs. These changes can start to occur within hours of a period of repeated synaptic activation by pain. In addition, the concentration of glutamate within the synaptic cleft is thought to be increased by the action of prostaglandin E2, PGE2, and nitric oxide. But the source is controversial, whether it's the glial cells such as the astrocytes or microglia, or from the neurons themselves. In neuropathic pain, it seems likely that it would be from the damaged neurons. Structural changes that can be seen quite quickly after a significant episode of pain include an increase in the number of the little synaptic spines on the dendrites and an increase in the size or number of the dendrites. Remember the A-beta fibers in gait control? They usually detect non-noxious touch, but in allodynia they are thought to sprout collaterals, little branches, that synapse directly with second-order pain afferents. So, no inhibitory interneuron involved as in gait control. Therefore, this is a pro rather than anti-nociceptive mechanism. So touch is perceived as pain. Remember descending modulation, how interneurons act as on or off switches or can even be silent in the PAG. Usually the upshot is the inhibition of pain via IPSPs in the second order afferent. In other words, the pathway is anti-nociceptive. However, in persistent pain, there are changes in the way that those interneurons behave, and silent ones can also become activated. The result in chronic pain is descending facilitation rather than modulation, and this increases pain, i.e. the descending pathway becomes pronociceptive. You may see long-term depression in texts. This is the opposite of LTP. In this case, synapses that are not stimulated become less responsive. It's often discussed in terms of the hippocampus and memory. So what does this tell us in terms of revision? Anyway, before I go over LTP mechanisms on whiteboard, I have to tell you that the subject is not only extremely complex, but it's also still the subject of research. The mechanisms I've mentioned here are not the only ones, and the research is really difficult to interpret because most of it is focused on the hippocampus and memory, or has applied to animals rather than humans. At the end of the day, you only need an outline knowledge in order to understand chronic or persistent pain states in a clinical context. You'll be glad to know.
Let's talk about long-term potentiation. In terms of the actual synapse itself, and this is synaptic plasticity, so here's our presynaptic up at the top. Let's just label that. And below we've got, and I'm going to make this nice and big because I want to write loads in it. This is our post-synaptic neuron. Okay, in terms of the presynaptic changes that we get in long-term potentiation, we talked about an increase in glutamate, and in studies they have noticed that there's an increase in glutamate released into the synaptic cleft. Two things that are known to do this, to increase our glutamate, if I can go there, increase glutamate. I'll come out there. Our good old friend PGE2 and our other good old friend nitric oxide. Both of these stimulate an increase in glutamate exocytosis. The question is, where do they come from? And that's a bit sort of still subject to controversy. There's talk of it coming from the astrocytes, there's talk of it coming from microglia. Remember microglia, the brain's macrophages. And there's also talk of it coming from the neurons themselves. And that might particularly relate to conditions where there's neuropathy, where there's damage to the neurons themselves. And of course, they're going to secrete PGE and nitric oxide. So in those cases, that's probably where it comes from. In other cases, could be the astrocytes, could be the microglia. So we're not entirely sure where it comes from, but it does increase glutamate. And if you increase glutamate, you're going to increase the stimulation. Okay, and we talked about calcium, the role of calcium, particularly when it binds to calmodulin and it becomes a signaling molecule. And if you remember, we get calcium influxing through the NMDAs, and we also get some of our metabotropic receptors are bound by glutamate. And remember old IP3? IP3, second messengers. So we get IP3 produced, binds to the endoplasmic reticulum, and we get a release of more calcium. So we've got all this calcium floating around, binding to calmodulin and becoming a signaling molecule. And in terms of our AMPAs, they mainly work on the AMPAs, or though there is some talk now that calcium does actually upregulate the NMDARS as well, but still a bit controversial. In terms of AMPAs, we get very quickly, we're talking within a few hours here, we get AMPA phosphorylation. If we get phosphorylation, we get sensitization. They open more readily. So we're going to get stronger EPSPs and more EPSPs. The other thing we get is an increase in the number of AMPAs. So we get more of them expressed. You remember the mechanism where we get exocytosis? They're made through protein synthesis, put in vesicles. Vesicles go up, flatten out, and we get more AMPAs expressed on our postsynaptic membrane. The other thing we talked about in terms of AMPAs was that they change. And actually what happens is the ones that we've got there get taken in that only let sodium through, and we put up some different ones that have got an extra little subunit, and that extra little subunit means that we have AMPAs that influx both sodium, as usual, and calcium. So we get these changes to the AMPAs. We get an increase in glutamate. The changes to the AMPAs are down to our calcium both influxed and released from the endoplasmic reticulum. In addition to that, we get structural changes. And in terms of our structural changes, we've talked about the dendritic spines. So where you get synapses, and we always draw them like this in the central nervous system, it's because you've got two little spines that synapse together. They stick out from the dendrites. So we get so in terms of structural, just make this clear, we're talking about structural here, we get an increase in the spines. If we get an increase in the spines, we've got more synapses on our dendrites. The other thing that's been seen, and been seen very quickly, surprisingly quickly, within only a few hours, we get larger or even more dendrites. So we get more of those projections from the soma, bigger ones, and on them we get more potential synapses, more little spines to synapse with. So we start to see these sort of structural changes. And in terms of allodynia, wonderful word, allodynia, isn't it? Allodynia. Sounds like you're saying hello to someone called dynia. In terms of allodynia, this is where our A-betas come in again. But in this case, they're not inhibiting because you're rubbing them. We have two separate pathways. So here's our little pain pathway, our normal pain pathway coming in, synapsing with our second order and dorsal horn, and on it goes. Alongside that, possibly in the same spinal nerve, we've got an A-beta. And if you remember, A-beta are mechanoreceptors on the ends of them, and they respond to touch. So that has its own little parallel pathway, which when it gets to the brain will say, yeah, I can feel something touching me. But part of the structural changes in long-term potentiation, it's suspected that allodynia is due to collaterals. So new branches grow, a bit like angiogenesis of vessels in terms of neurons. This happens with the A betas. And it's believed that they grow these new collaterals that eventually will synapse with the second order neuron of the pain pathway. Now, when we talked about gate control, we talked about A betas, you rub it, and it creates an EPSP by using an inhibitory interneuron. In this case, it's actually going to produce an EPSP. So it's pro-nociceptive in this case, not anti-nociceptive. But if you think about this in terms of allodynia is the perception of non-noxious stimuli, in other words, something touching you, as pain. I don't know about you, but when I'm not very well, if someone touches your skin and it's ultra-sensitive and it feels like pain. And that's what allodynia is. You get a sensation that should be perceived as touch. Because you've got a collateral creating an EPSP in a second order of the pain pathway, that touch is then perceived as pain. And that's thought to be the mechanism of allodynia. So we've got structural changes and we've got synaptic changes.
As for the consequences of pain, they can be both physical and psychological and can be extremely debilitating. I hope you've enjoyed the 2 parts of this e-lecture and have met the learning objectives set out in part 1. We'll revisit aspects in terms of specific systems or disorders during the clinical reasoning module, so please ensure that you are familiar with the topic. If you have any queries, please feel free to email me.